So we can make all kinds of diagrams with entropy. If it's a property that can be measured, and it can be measured indirectly, then we can make a TS diagram. We can make a PS diagram if we want. But most often, we will be interested in TS diagrams. If we have a substance where we're investigating the region where it can change phases, then we'll see the vapor dome like we would with any other property, and we can make tables of data, we can make graphs of data, and so forth that represent the nature of the particular chemical substance that we're working with. An interesting thing that you would note if you make a TS diagram is that the pressure lines, the lines of constant pressure for our various boiling experiments, would be almost on top of the saturated liquid line. Another interesting feature is, of course, under the vapor dome, just like expected, the pressure line is parallel to the temperature line. Again, what's happening here is that these are two things that depend on one another. We can only have 1 degree of freedom because we're under the vapor dome with 2 phases. And then finally, in the superheated region, the lines of constant volume are actually steeper than the lines of constant pressure, but not by a whole lot. So this is not really anything different than what we've seen before. And I don't show you this because I expect you to remember it or understand it in great detail. I show you this because I'm trying to convince you that entropy is just another property that will be useful for us. The TS diagram itself, though, is particularly interesting because if we know a process path that is internally reversible, we could consider what the area beneath that path means. It has a very important meaning. Remember that in our equation we defined an entropy change ds as the ratio of dq over t, where dq was a small amount of heat transfer to the system at a temperature T. Well, we can rearrange that equation and say that the amount of heat transfer, the differential amount of heat transfer dq, is equal to T times ds. Now, if we look at the graph, ds is just the differential change in entropy across the horizontal axis, and the temperature T is essentially constant since the differential entropy change is small, and so that T times ds is just the area of a rectangle. This is just area. So the area underneath this whole curve represents the integral of all the heat transfer that occurs during the process, and so it's just Q. It's the amount of heat transfer. Just like on a PV diagram, the area beneath the process curve represents work. On a TS diagram, the area beneath the process curve indicates the total amount of heat transfer, at least for an internally reversible process. And all this comes from our definition of entropy, and all we did was just rearrange it a little bit. We noted that the term on the right hand side is a fraction. We just move the temperature to the other side and have this nice interpretation of area beneath the process curve on the TS diagram. So once we've rearranged it, then we realize that this area is something that has a physical interpretation. There are special cases, just like with boundary work. We went through and we found several different integrated forms of the boundary work equation, which was, boundary work equals the integral of PdV. One thing I didn't point out very strongly at that time is that the boundary work equation assumes reversibility. It also is only good for an internally reversible process. I'm not talking about what's on the screen yet. We're going back and talking about the boundary work equation that is the integral of PdV. Well, in that, think about it. We used it for piston cylinder devices quite a lot, right? So if we had a piston cylinder device, and let's say the gas was doing work expanding the system and pushing the piston upward, well, the amount of work we get out of the system we think we can calculate by integrating PdV, right? The only problem with that is, what if there's friction? What if there is an irreversibility present in the system? What if the gas expands quickly? That's an irreversibility. All those irreversibilities means that ultimately the work we actually get out of the piston will be less than the maximum work that we should have gotten out of it. We'll be cheated a little bit by irreversibilities. So that boundary work equation we've had and all our integrated forms are actually also for internally reversible systems. And that's interesting because this equation that we're playing with now, the integral of TdS being the amount of heat transfer, it also has to be internally reversible to be true. So there are particular processes on the TS diagram that have special shapes, and it makes integrating the area underneath the process curve very easy. For example, consider a vertical line on the TS diagram. Well, on the TS diagram, a vertical line would have no area beneath it. So that should be easy to integrate. right? So it's just zero. As a matter of fact, we can say some things about this process because we know it's a vertical line. That means its entropy doesn't change. This is an isentropic process. Since there's no area beneath the process curve, well, that means there's no heat transfer, so this is also adiabatic. Furthermore, this is a reversible process, okay, because it doesn't generate any entropy. Therefore, it must be a reversible process. Notice the entropy at the initial and final states are equal, so no entropy was generated during this process. Now, the curve on the right-hand side is just a horizontal line, and the area beneath that process curve is easy. It's just a rectangle, right? So we just need the temperature, T naught. This is a constant temperature process. And we need to know the change in entropy. And if we do that, we can calculate both, either the total heat transfer or, if we know the specific entropy change, we can calculate the heat transfer per unit mass. And so that's really easy to integrate. And the one on the left is easy. It's just zero, right? It's no big deal. Now, these are special cases, but they will be useful to us, in particular when we encounter the Carnot cycle. And the one on the right will be useful for several other situations as well. So what about entropy? Can it be transferred? Well, as a matter of fact, it can. Heat is something that carries entropy with it. And this is a key concept and a key fact that I want you to remember. Heat always carries entropy with it. As a matter of fact, consider a system where the temperature of the system remains constant. Maybe there's a liquid inside that's boiling off and we're transferring heat into that liquid. Let's say we transfer 500 kilojoules and we do that transfer at 400 Kelvin, so that's the temperature. Because this is a constant temperature process, as we saw on the last slide, you can actually rearrange the equation. Instead of talking about the heat transfer equals the entropy change multiplied by the temperature, you can rearrange it and figure out how much entropy goes into the system, because it's just Q over the temperature at which that heat was transferred. Because understand, this is an internally reversible process, and so the heat that's transferred in could be transferred back out, right? And the entropy change in that cycle would be zero. There's no entropy being generated here, okay? At least not internal to the system. Rather, entropy is simply being transferred into the system. So we can calculate that amount of entropy by just taking the amount of heat transfer and dividing by the absolute temperature of that heat transfer. Okay? Okay, so if that's true, then heat carries entropy with it. And couldn't heat also carry entropy out of the system? Well, yes, it can, right? As a matter of fact, if the heat transfer is positive going into the system, then the entropy change will be positive. If the heat transfer is negative, in other words flowing out, the change in entropy will be negative. That doesn't mean entropy has been destroyed. It means that entropy has been extracted from the system, and that is certainly possible. If that weren't possible, we couldn't build engines, because we have to have engines that operate on a cycle, and since we can't destroy any entropy we generate, we've got to somehow get rid of it. That's actually the main reason why your car dumps so much heat out the tailpipe. That's why it wastes so much energy, because it has to get rid of the entropy that has been generated. Mass can also carry entropy with it. Mass carry, if for entropy to be a thing, something has to hold it, right? And it's mass that holds it. So, if you transfer a fluid into a control volume, obviously it must carry entropy with it. That's without any mass, a system can't have any entropy. It doesn't even make sense anymore, right? Because entropy is just how many ways essentially that the energy can be distributed within the system. Well, if there's nothing to hold the energy, then there's no entropy to talk about. Okay, so mass can certainly carry not only enthalpy with it, but also entropy. Now, why did they name them enthalpy and entropy? I have no idea. It's unfortunate that the names sound so similar, but we use H for enthalpy. Some people will express it that way to make it very clear they're not saying entropy. I just say enthalpy. And entropy, right? We give the symbol S to entropy. So you have to listen carefully to understand which one is being discussed. Interestingly enough, work does not transfer entropy with it. Now, work can be used to generate entropy. For example, if I have a vat of bubble gum and I'm stirring it up with a stirring rod, obviously what's going to happen is there's going to be a lot of friction, there's going to be a temperature increase, and all the work that I'm putting in will be transformed into thermal energy, and that is an irreversible thing. I would never expect hot bubble gum to drive a propeller and let me get work out of it, right? So the entropy, though, was not transferred into the system by work in that case. Rather, the entropy was generated by friction. Friction is the irreversibility itself. Now, this is the fundamental reason that work is more valuable than heat. It's because work can be transformed into heat completely, but heat cannot be completely transformed into work. It depends on what temperature differences you have available to work between as to how much of the heat can be transformed into work. So work is a really valuable form of energy. That's why electricity is a valuable form of energy. It's a form of work. And so entropy is not transferred with work, but is often generated in systems that do work. Even this, I've shown this in a piston cylinder device, maybe we're stirring water around or heating up air by simply moving this paddle in it. Obviously, we could get some work back out, but we won't get as much work out as we have to put in, because there's going to be some waste energy, some low quality energy left in the, if we think about it being air, and we're turning this propeller so fast that we're generating extreme vortices where the air's internal friction or its viscosity ends up warming the air so that the piston can do work as the air expands. That's all well and good, but the amount of work we get out of that piston from boundary work is not going to be equal to the work we put in, because some of it's going to stay behind as thermal energy in the air that simply can't do any more work. So entropy is certainly generated in that process because we're getting less work out than we put in. If we want the work to come out, it's better just to couple up a shaft and continue through this system, right? So that the work we get is simply never transformed into some other form. As a matter of fact, it's a general principle that every time you transform energy, one of the reasons that you lose some of it, it's not destroyed. What happens is entropy is generated, and some of it goes off as waste heat. If you think about an alternator, for example, this should make a lot of sense, because you put shaft work into the alternator and you get electrical work out of it. And yet, have you ever noticed that there's a fan on the front of an alternator and cooling holes in it? Well, where does that energy come from? Well, it came from gasoline that you paid for at the pump that was converted to thermal energy in the engine, that was converted into work, that then drove the alternator, and then changed back into some thermal energy, right? And you need to take it out so that the alternator keeps functioning. So the amount of electrical work you get out of the alternator is less than the amount of shaft work that went into the alternator. And the reason is because of friction, for one thing. Of course, bearings are used to minimize that. But you've got current flowing through copper wires. Copper has some resistance. That's another irreversibility. And all these things add up so that the transfer of energy from one form to another, both even being a form of work, right? Shaft work to electrical work, is not 100% efficient. And so one of the big principles I want you to get out of this class is you really want to minimize the number of times that energy changes form. We talked a little bit earlier about the fact that maybe a gas water heater is better than an electrical water heater, even though the electrical water heater might have a 100% efficiency. As a matter of fact, the gas water heater may have only 55%. But think about it. The fuel for the gas water heater did not have to go through and drive a turbine, for example, down at the power plant to generate electricity, to then go over some lossy power wires to your home, to then go into your water heater and heat up the water, right? As a matter of fact, at my house, I've got an electric water heater, and it's probably, you know, a third or so of my electric bill. I can't wait to get rid of it. And actually, I'm going to keep it, but what I'm going to do, I've already hooked up a heat exchanger called a sidearm on it, and what I'm doing is just plumbing it into my boiler, because what I'm going to do is transform chemical energy in wood to thermal energy and immediately put that into the water. Now, it helps that the wood is very inexpensive. It's a lot cheaper per unit of energy than the electricity is. But the general principle here is that I'm trying to reduce the number of times that the energy transforms into some other form, and thereby increase efficiency, and hopefully lower cost as well. So in this process, with this work going in and entropy being generated by friction, there's certainly entropy being generated, and therefore this is irreversible, and that's the reason it's irreversible. The Carnot cycle on a TS diagram takes on a much more reasonable shape. On the PV diagram, it looks kind of strange, but on the TS diagram, it just seems to make sense. If you think about all the processes that it consisted of, we had an energy source that was transferring thermal energy into the system at a rate so that the temperature remained constant as the piston expanded doing work. And so from state 1 to state 2 we have a volume increase, but we also have an entropy increase. Even though the temperature remains constant at TH, we're transferring heat into the system, and therefore the entropy of the system is going up even though the temperature is not. So there's our reversible isothermal expansion that's occurring with heat transfer just to maintain the temperature constant. The next process from state 2 to state 3 is an isentropic process. Well, remember, it's reversible and it's adiabatic. Now, what does that mean? If it's reversible, well, that means it's not generating any entropy. If there's no heat transfer, then again there's no entropy change of the system. Therefore, this is an isentropic process. It's a vertical line on the TS diagram. Even though the temperature drops from TH to TL, this is a completely reversible process. Remember that all these processes literally take eternity to actually occur. But this Carnot cycle tells us the absolute limit of what we could ever hope to achieve, even with the limitations that thermodynamics puts on us, in particular that entropy puts on us. From state 3 to state 4, remember the piston was being pushed in, work was being done on the system, but waste heat was being transferred out of the system. Notice that now we have some energy that has a lower quality. It has less usefulness to us. And so it is waste energy that must be transferred out of the system in order to operate this extremely ideal system on a cycle. Okay? So what we've got is a low temperature sink where we are doing reversible isothermal compression, putting work into the system, maintaining the temperature of the air or whatever gas or whatever the fluid may be that's operating on the piston. We've got it remaining at a constant temperature. So this is an isothermal process where heat's being transferred out. Therefore, the entropy of the system is going down. This is the whole key to the process, being able to cycle, right? Being able to tag all these processes together and make a cycle out of it. This is the key. We've got to get rid of some entropy, and this is where we do it. Okay? No entropy is being generated, but we've got to get rid of the entropy that exists in the waste energy. And then finally, from state 4 to state 1, we've got a reversible adiabatic compression occurring. Remember, we've put insulation on the surface of the piston again so that there's no heat transfer, and since there's no heat transfer and this is reversible, then that's another indication it must be a vertical line. So we are compressing the system, putting work into it, increasing the temperature, which makes sense. If work goes in, it's energy. It's got to come in and go somewhere. So it would increase the temperature of the gas, and we end up back at state 1 so that we can run this cycle again and produce a net amount of work without breaking the Clausius or Kelvin-Planck statement of the second law. The point here is that as heat is transferred, it carries entropy with it. And so if we want to put heat in to get some work out, we have to accept the fact that some entropy is going to come along with it. And to get the system back to where it started, in other words, to operate it on a cycle, we will have to transfer heat out and thereby get rid of that extra entropy of the system. Now, one interesting thing about this is that the net amount of work produced by the cycle will be the difference between the heat flows. We knew that from before, or by an energy balance around the cycle. The other interesting thing is that the area beneath process path 3 to 4 is QL. The area beneath process path 1 to 2 is the whole rectangle, not just what's inside of the cycle, but the entire rectangle down to the entropy axis. And the difference between those two is literally the difference between the areas, which is literally the area inside of the cycle. So again, just like on the PV diagram, the area enclosed by the cycle diagram represents the net amount of work we get out for an internally, at least internally reversible cycle. In this case, a totally reversible cycle.